Now that we have some basic physics infrastructure in place, it's time to start looking at particle collision. This topic actually includes two things: collision detection and collision response. First, you need to detect that a collision has occurred, and then you need to respond to it. Many objects are composed of thousands of vertices, so it's almost always impractical to do collision detection at that level. This is why most games use a much coarser technique of creating bounding shapes which encapsulate the entire object. Checking for collision with these shapes is much simpler than working at the vertex level. Some of the most popular shapes are spheres, axis-aligned bounding boxes, and capsules. Spheres are probably the simplest shape to implement, so that's what we're going to use today. To create a bounding sphere, we need to find some point roughly at the center of the object, and then choose a radius so that the resulting sphere encapsulates the entire object with minimal extra space. Creation of the bounding sphere is a source for many algorithms, which are out of scope for this tutorial. So I will assume that the center of the sphere is equal to the center of mass that we have in our point mass class, and the user is expected to provide a radius. In today's demo, we will be using spheres for the objects, so in that case the bounding sphere is identical to the object it bounds. Before we get started, I'd like to say a big thank you to Venkatesh, who recently joined 3D Underground. If you too would like to support this channel, you can do that at patreon.com/ogldev or by joining the YouTube channel as a member. Detecting a collision between two spheres is very simple. Find the distance between the center of the spheres and compare it to the sum of their radiuses. If they are equal, it means that there is a single point of contact between the spheres, and we can consider this to be a collision. If the distance is smaller, then the spheres are intersecting, so we should handle the collision as soon as possible before the objects render on top of each other. If the distance is greater than the sum of the radiuses, there is no collision, plain and simple. To implement this algorithm, I've added a bounding radius variable as a private attribute in the point mass class, as well as a public function to modify it. As I said, I assume that the center of mass is also the center of the bounding sphere, but of course you can always add a separate variable for that. There is a new private function called checkCollision, which takes a reference to a point mass object as the particle that we want to check collision with, and returns a Boolean flag which indicates that such a collision has occurred. In this function we use the GLM length2 function to calculate the distance between the centers of the two spheres. The regular version of length performs a square root over the sum of the squares of the vector components. Length2 drops the square root, so we are left with just the sum of squares. This is a minor optimization which is very popular. To compensate for the square root, we raise the sum of the radiuses to the power of 2, which is much less expensive compute-wise. We can now compare the two values. If the distance squared is less than or equal the sum of the radiuses squared, we have a collision. Now what about collision response? In the real world, objects may crack and deform, and some heat is often generated as a result of a collision, but this is too complex to implement at this early stage. Instead, we simply assume that after the collision, the two objects fly off in different directions. So we know the masses of the two objects as well as their velocities at the point of impact. We assume that the masses don't change as a result of the collision, so we just need to calculate the velocities after the collision. Let's introduce a new concept, momentum. In simple words, momentum describes how hard it is to stop a moving object. As you can imagine, the answer depends on the mass of the object and how fast it is moving. Think about stopping a bicycle compared to stopping a big truck. The speed of the truck may be just 5x more than the bicycle, but its mass can be 1000x or even more. To calculate the momentum, we multiply the mass by the velocity. This means that momentum is a vector, which is always aligned with the velocity vector. An important principle in physics is the conservation of momentum, which says that the total momentum of a closed system remains constant unless an external force acts on it. This means that if we ignore outside forces such as friction, we can say that the combined momentum of the objects is the same before and after a collision. So we can write the following equation, and if we replace the momentum by the product of the mass and velocity, we get this. But we have just one equation and we want to solve it for two variables, the velocities after the collision. So we need another equation. Enter kinetic energy. This is the type of energy that an object possesses as a result of being in motion. Naturally, a stationary object has zero kinetic energy. If an object travels along a straight line, we can calculate its kinetic energy as follows. In a similar way to the conservation of momentum, we also have the principle of the conservation of energy. The total energy of a closed system remains constant. Energy cannot be created or destroyed. It can only be transferred between objects or converted between different forms of energy. In our case, the collision causes an energy transfer between the colliding objects. Based on this principle, we can say that the sum of energy before the collision is equal to the sum of energy after. Let's replace capital K with the equation of kinetic energy, and we get the following. We now have two equations involving the same set of variables. I'm going to skip quite a few steps of substitution and rearrangement, but eventually we can extract the following equations for calculating the velocities after the collision. Now let's talk about the types of collisions that we can expect. There are two extreme cases here, elastic and inelastic. A perfectly elastic collision means that no kinetic energy is lost. The objects simply transfer some energy between them and then bounce away in different directions. This idea is kind of represented by the pool table. In a perfectly inelastic collision, all the kinetic energy associated with their relative velocity is lost. The relative velocity is the difference between the two velocities before the collision. So the relative velocity of object 1 with respect to object 2 is v1 minus v2, and the relative velocity of object 2 with respect to object 1 is vice versa. The result of a perfectly inelastic collision is that the objects stick together and share the same post-collision velocity vector. An example is when the material is sticky or deformable in some way that makes the objects stick together. Along the spectrum between the two extreme cases of the perfectly elastic and perfectly inelastic collisions, there are infinite cases where some energy is lost, but the objects don't stick together. This brings us to the concept of the coefficient of restitution. This coefficient measures how bouncy the collision is. It goes between 1 for the perfectly elastic and 0 for the perfectly inelastic. It is basically the ratio between how fast the objects separate after the collision and how fast they were approaching before the collision. The equation is as follows. Notice that the order is reversed between the numerator and denominator. This is because the approach speed is v1 minus v2, which means that object 1 is moving towards object 2, and the separation speed is v2 minus v1, which means that object 2 is moving away from object 1. When the coefficient of restitution is 1, the separation vector is simply the opposite of the approach vector. When the coefficient is 0, since the denominator cannot be 0, we have to conclude that the post-collision velocities are the same, which is why they stick together. The coefficient can be measured empirically, for example, by dropping a ball and taking the ratio between the height from which it was dropped and the maximum height that it reached after hitting the floor. Here's an example of a few cases. Given the equation that we have seen based on the conservation of momentum and the equation of the coefficient of restitution, we can derive the post-collision velocities as follows. Now, I have to tell you something really important. Everything that we have seen so far is in one dimension. This means that objects can only move forward or backward along the collision normal, which is the unit vector that goes between the centers of the two spheres at the moment of impact. Think about two balls sliding towards each other on a straight track. So how can this be even useful in the real world? The answer is that we calculate the collision in 1D and then project it back to 3D to be used for the actual simulation. The process is as follows. We start by projecting the two velocity vectors on the collision normal using a dot product. This gives us the length of the projected vectors along the collision normal. Remember that the normal is pointing from one center towards the other, so when we project the two collision vectors, the result will be positive for the originating sphere and negative for the destination sphere. When we multiply the results by the same normal vector, we end up with the two projected vectors pointing at one another. This is the 1D vector that I talked about in reference to collision calculation, and we can plug it into the previous equation in order to calculate the post-collision 1D vectors. These vectors now point in the opposite direction of the original projections. To go back to 3D, we subtract the original projection from the post-collision projection. Since they are opposite to each other, it's the same as adding them together, as if they are pointing in the same direction. We can now multiply this sum by the normal vector and add to the original velocity. This gives us the post-collision vector in 3D. To implement this algorithm, I factored out the existing code of the update function to its own private function called updateInternal. After executing this guy, we call a new function called handleCollisions. This function checks for collision between each pair of particles. Notice how the external loop goes over all the particles, but the inner loop only traverses from the current particle until the end. This is to avoid checking the same pair twice. Obviously, this brute force approach can explode very quickly if you have lots of particles. We can optimize it in different ways, but for now, we assume that we don't have so many particles, so the CPU can handle it this way. I've added a function called handleCollision to the pointMass class, which takes the particle that we want to check collision with as a parameter. To handle a collision, both radiuses must be greater than 0. This allows you to skip certain particles if it doesn't make sense in your game. We start by calling the function that we have already seen to check whether a collision has occurred. If it did, we execute the algorithm step by step exactly as it was described, calculating the collision normal, projecting the two velocity vectors on this normal, calculating the post-collision projection, and then going back to 3D. I would like to point out a couple of important things here. We don't use the normalize function to calculate the collision normal. Instead, we calculate the full vector and distance separately. Then we continue only if the distance is greater than 0. This seems highly unlikely to occur, but due to numerical instability as well as an error that brought the particles to the same location, it seems safe to check it. The distance can now be used to normalize the vector. Next, we have another potential early exit. If the particles are already separating from each other, we don't have to continue with the full calculation. We calculate the relative velocity of the two particles. So if you are sitting on the other particle, this tells you how the current particle is moving with respect to it. We do a dot product between the relative velocity and the collision normal and check the sign of the result. Remember that the collision normal is pointing from the other particle to the current one. If the current particle is moving towards the other, then the normal and relative velocity will be opposite to each other, which means their dot product will be less than or equal to 0. But if they are moving apart, the relative velocity will point to the same direction as the normal, so the dot product will be positive. This means that we only need to continue with the algorithm if the dot product is less than or equal to 0. So in the case of a collision, the velocity vectors of the two particles will be flipped, and in the next frame will be used to calculate the new position. This allows us to implement a simple minigame where one ball is going across the screen, and by clicking on spacebar, we launch another ball towards it. When the two balls hit, we can verify that the collision code actually works. Let's test different values of the coefficient of restitution and see how they affect the behavior of the demo. As you can see, when the coefficient goes down, some of the energy gets lost as a result of the collision, and they continue roughly together. Let's set the coefficient to 0 and see if they stick. Unfortunately, they don't. This is because we are still calculating the velocities independently. Therefore, I've added a check for this case, and when that happens, the velocity is shared between the particles, which guarantees they move together. So that's it for today. If you enjoyed the video, please hit the like button and subscribe. Thank you for watching, and I will see you next time.